Back when we first met data, we differentiated between discrete variables and continuous variables. Discrete variables were such things as the number of heads and 10 flips of a coin, or the number of aces in a card hand. These variables were counting numbers only, sometimes called whole numbers. We also met continuous data, or random variables. These were numbers that could be divided and divided again and still have a true meaning, such as an hour becomes 60 minutes, 60 minutes becomes 60 seconds, and so on. This last unit dealt with probability distributions for discrete random variables. In every case, the variable we were interested in could not be divided and still retain its meaning. No such thing as half of a phone call to a fire station. We did meet the Poisson probability distribution, which creates a discrete random variable from a continuous random variable, usually time or space. The continuous random variable, say time, was divided into discrete intervals for which probabilities could be calculated. We did have to assume that the discrete pieces were of constant size and the event did not overlap. This device, as clever as it is, did require these severe constraints. This limited the application of the discrete probability density functions we studied to the specific types of experiments that had discrete random variables. Much of the data we are interested in is not discrete. This includes virtually all the data relevant to business and economics questions, from interest rates, rates of return, cost of production ratios, and on and on. Measures of production are made in units that are continuous random variables, from kilowatt hours to barrels of oil pumped. We need to develop probability density functions that can handle this type of issue. In this unit, we will begin to do just that with the help of two probability distributions for continuous random variables. The first is the uniform distribution. This helps solve interesting cases where the probability of an event is equally distributed across the values of the random variable. An example would be for rolling a die. The probability for each face is the same, or called uniform, and is, of course, 1/6. The second is the exponential probability distribution. This distribution is much more useful and can calculate probabilities for the duration of time until a particular event occurs. It describes the amount of time a product will last until failure, duration of phone calls, how long it will take checking out from the store, and many other interesting examples. The king of all distributions, however, gets its own unit. This is the normal probability density function, and will be the foundation for all that follows in this course. We will meet this distribution in the next unit.